So last time I mentioned that if f is differentiable, if you have f prime x, then the derivative is a linear map, like this, and so that means in the standard basis it has a matrix representation. And I mentioned that the partial derivatives are going to come up when you try to write down the components in that matrix representation. So this theorem, theorem 9.17, is going to tell us how that actually happens. So suppose you have this function, and it's differentiable at x. And assume, yeah, that's it. It's differentiable at x. Then it follows that the partial derivatives exist. That's going to be easy for us. We pretty much already proved that. But also, what we're going to say is, what this theorem will tell us is, in terms of the partial derivatives, what are the components of this matrix, of this linear map? It will tell us what are the components in the matrix representation for this linear map in the standard basis. So if I want the components of a matrix representation of a linear map, I should feed the basis vectors in like this. So let me feed in the jth basis vector, and then in the output I should write down the output as a linear combination of the basis vectors for the codomain of the linear map. Those are what I refer to as the u sub i's. So from I equals 1 to m, u sub I, and then whatever coefficient goes here, that's going to be telling us what are the matrix components when you write things, when you express this linear map as a matrix. So here's what theorem 9.17 is going to tell us, that dj fi of x, that this is what goes here. Okay, so let's prove this. So assume the hypotheses. Now, there's a lot that we already got done from last lecture. So in lecture 2, we proved that, in fact, for any vector v in Rn, so it doesn't have to be a standard basis vector like this one, we have f prime x at v is the directional derivative in the v direction of f at x. So that means in particular we have this for the special case where v is one of the standard basis vectors. So in particular, f prime x v is d sub ej. Sorry. The whole point is if I put ej here, then I get d sub ej of f at x. Alright, so we're actually kind of almost done. But what I wanted to get on the right side was this sum up here, right? So it remains, by the way, I should have said fix j up here. Fix j, 1 through n. So now it remains to prove that this directional derivative is equal to that sum. Okay. And part of our proof, I guess, is to also show that these exist. So we know this exists. That was part of a previous lecture. But also we still need to show that these exist, in addition to showing, after they exist, that this equality holds. So in fact, this E sub j here is kind of clutter in this situation. In fact, we can verify for any v. It doesn't have to be E sub j. We can verify for any v that d sub v f x can be written like this, has these components: d sub v fi sum over I. So let's just get this clutter E sub j out of the way and just focus on an arbitrary v. We should be able to do this. So let's work on trying to prove this. So by definition of the directional derivative, this will be, so this is what I want to prove here. And the left-hand side, by definition, will be d dt f of x plus tv at t equals 0. That's the definition of this directional derivative notation. So that means we have the limit as t goes to 0 of f of x plus tv minus f of x plus 0v, all divided by t. So we already know, in our reasoning, we already know this limit exists. In other words, we already know this derivative exists. We already know this directional derivative exists. We already know those things because we are referencing what we proved in a previous lecture. This reference to lecture 2 here is that is a reference to the fact that when we know f prime of x exists, that this total derivative f prime of x exists, then it follows that any directional derivative exists, and the directional derivatives are given in terms of f prime of x, like this. So we're in a situation where we already know that this limit exists. We're trying to show that these individual limits here exist and are related in this way. Okay, so now f is a function with multiple components, right? So this thing here is an m tuple, m, it's hard to hear that and distinguish it from n, m tuple valued function of t. So that means it could be decomposed into its components. Let me express that this way. It's a sum of its components. And the components can be written in terms of the component functions of f, like this. Okay, so this is something you can do to any vector, any m tuple. You can do this. So all I'm doing, let me just write this on the side. All I'm doing is if I have any w in Rn, I can always say w is the sum of the components of w times the standard basis. Right? So that's all I'm doing, and I'm applying it to this. This is playing the role of w. All right. Now, what do you want to do? You probably want to swap these, right? So is that justified? Can we just swap those? In other words, if you have a vector valued function, or a function with multiple components, is what I mean by that. If you have a function with multiple components, then when you take the limit of the overall function, is that the same as taking the limit of the individual components and then looking at the resulting tuple? Yes, it is the same. When all the limits involved exist, it's the same. I wanted a reference in Rudin for that, but I couldn't find one, actually. It's weird that that wasn't just stated as a theorem somewhere, but we can piece it together out of some parts. So let me show you. Okay, so here I've got baby Rudin, and this is where he starts talking about limits of functions, and that's it. What I just scrolled through, that like 2 pages right there, is all he's got. So there's not that many theorems available. Immediately after that, it's all about continuity. But what we can do is use this one. So theorem 4.2 here says that, let me see if I can make this look better. Theorem 4.2 says that you can use sequences to reason about limits, basically. So if you have a function of metric spaces in a situation where it makes sense to talk about limits, then limit of f as x goes to p is q if and only if this statement holds for every sequence that converges to p and is never equal to p. Okay, I don't think I need to spend too much time on this. You've seen it a million times probably. But basically, we can use this along with the next thing I'm about to show you. So over here, looking back in the chapter on sequences, theorem 3.4, if you have a sequence x sub n of k tuples here, and you write down all the component sequences, then your sequence of k-tuples converges to a particular k-tuple if and only if each component sequence converges to the corresponding component. And this is an if and only if. So we could use that with the other result about limits that lets you reason about limits in terms of sequences to get that result, which allows you to say, okay, here in this context, the limit of this m tuple is going to be the m tuple whose components are given by taking limits. Like this. All right. And now, what do we have here? So let me use the power of copying and pasting. Here, these limits are, well, the first way to write them maybe is they're the derivative with respect to t at t equals 0 of fi x plus tv. But we have another way of saying that. It is d sub v, the directional derivative in the v direction of the function fi evaluated at x. And that's what was needed. So that finishes the proof. And I forgot what we were even proving. Ah, right. So now we know about the matrix. Now we know this. We know about the matrix components when you try to represent this linear map as a matrix using standard basis. So this tells us how to represent f prime x by a matrix when f prime x exists. And let me just write down the matrix. So this will be a linear map, Rn to Rn. And so it'll be represented by an m by n matrix. When you use the standard basis. So how do I do this? So the first column will be f prime x evaluated at the first basis vector, the first standard basis vector. That will give me the first column. So somehow I have to take this f prime x of E1. That will be some m tuple, and that will be the first column. And then the second column will be that E2, and so on for the n columns, f prime x, En. So if I write it neatly, let me just write it, let me write the first column here neatly. This would be, we have found in the previous theorem that this would be D1 f1 of x. Then d1 f2 of x, and so on, up to d1 fm of x. So hopefully you're seeing why it's an m by n matrix. Just like this. So to summarize this theorem, 9.17, we've now seen that when f prime of x exists, when f is differentiable at x, the partials then also exist, and the relationship between the derivative of f at x and the partial derivatives is that the partial derivatives are the components of the matrix representation of f prime at x in the standard basis. So this is a one-way result. Right now it's just saying if f prime exists, then the partials exist, and you can then relate them in this matrix. It's not giving you the converse. So the converse actually does not always work. It's a little bit more complicated. But that's something we'll start working on in the next lecture, hopefully. Not in the next part of this lecture, but in lecture 4 for Monday. We will look at what's needed in order to get knowledge about the partial derivatives only to tell us that the overall derivative exists. So it does not always work. In fact, I think I'll give you guys an option of a presentable problem where you find an example where all the partials exist, and there's nothing wrong with the partial derivatives, but the total derivative still doesn't work out. So, yeah, I mean, even if you can build this matrix using the partials, that does not necessarily imply that that matrix is this total derivative, or that matrix, when you turn it into a linear map, gives you something that works as f prime x.